distance against time, then what do you notice? If you want to look at the change in time and the change in distance, what do you got? You actually got a slope of a line, right? This is slope, rise over run, change in distance over change in time, distance over time. So you got a slope. So automatically we see a really neat thing. We see that the average rate of change between 2 points is equal to the slope of the line connecting them. Well, that's really cool. By the way, what about lines? Maybe you forgot about lines. Well, let me remind you about lines. Okay, no problem. We can do lines. We can do lines. Lines, y minus y1 equals m times x minus x1. This is the point slope form. All you need to give me is a point on the line, x1, y1, and a slope, m. You give me those two pieces of information, I can always write down the line uniquely. Always, always, always. Never forget it. Okay, fine. So now we're back to here. Now we can find average rate, and what do we see? Well, in fact, a line that touches the curve at 2 points is sometimes called a secant line. So in fact, we just discovered that the average rate, change in distance over change in time, is equal to the slope of the secant line. Cool. So all you have to do, you want to find average rate, connect the 2 points with a line, find the slope, you got the average rate. No biggie. But that's not what we want. We want instantaneous rate. So how do you do that? Well, what would that be? Well, if I want to find instantaneous rate here, what would I do? I'd make that secant line closer and closer and closer, bring these points together, and look what I'm converging to. I'm coming to a tangent line. Wow. Instantaneous rate of change equals the slope of the tangent line. So what we want is slope of tangent line. Well, what's the slope of the tangent line? It's change in y over change in x, change in distance over change in time. But now the change in time from that point to itself is 0. 0 over 0. So I'm getting 0 over 0, which is complete garbage, and that is a big problem. Our first major problem of the course. Okay, so what do? Well, we can that. Distance equals rate times time. We're going to can that. Instantaneous rate of change, I really want that. So what do? Well, how do we get that 0 over 0 problem to go away? The answer is we inch up to it. We just approach the 0 point. And what would that look like? Well, let me remind you what you've done when you were a little teeny kid. When you were a little teeny kid, this is what you were looking at. You were looking at a value of function at a point. Value of function at a point. Okay, not a big deal. There it is. F of A, it's that point. But you don't know anything else about the function. You don't know what's going around there, because all you're looking at is F of A. You open it up, woohoo, the function will be quite interesting. Who knows? Okay, but now what I invite us to do, and what calculus invites us to do, is to look at the function this way. Cover up that point and look at everything else. Open the window, look outside. That's where calculus is. And what you see here is we can see what things are approaching, and we can actually determine the idea of a limit. The limit is what things are approaching. We don't care about what actually happens at that point, only what things are approaching. Armed with the idea of a limit, what can we do? Well, now we can return to the question and figure out, let's take the limit as delta t goes to 0. What do we get? We get 0 over 0. That is called an indeterminate form when you get 0 over 0. So what do? You've got to do some algebraic gymnastics. You can either factor the top and cancel with the bottom. You can try to multiply by the conjugate. You can try to combine the fractions. There's all these tricks into the trade to actually reduce this to something that you can actually find. So you find the limit. Okay, well once you find the limit and you take the limit as delta t goes to 0, what do you get? You get the answer to the question, how do you find instantaneous rate of change? The answer is what we call the derivative. And what's the derivative? It's the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Looks pretty confusing, doesn't it? It's just rate. It's distance over time, but now I'm letting the time go to 0. Not a big deal. So that's the derivative. Bingo. We're done with the first question. And so now what do we see? Well, we see now that we come back to here, and the derivative, in fact, gives us the slope of the tangent line. Well, that's really cool. If you want to find a slope of a tangent line ever in life, you just take the derivative, and that gives you the slope of the tangent once you evaluate it at the point you want. Great. But for free, we answer the first question, because remember, the derivative also represents the instantaneous rate of change. So you want to find out how things are changing? No big deal. You take a derivative, plug in, and that will tell you how things are changing at that instant. Okay, great. So now we know all about how to graph these things, how to look at these things, the derivative, instantaneous velocity, boom, boom, boom. We got it all on the way. Now let's take a look at some applications. What can we do with this? Well, how would you take derivatives of complicated functions? Well, if you got a product, you need the product rule. Remember the product rule, don't memorize the formula, memorize the chant. First times the derivative of the second plus the second times the derivative of the first. So the derivative of a product is this. It's not the product of the derivatives. You got to use the product rule. We've got 5 minutes this minute up here, folks. I got to move faster. What if you have a quotient? Well, then you use the quotient rule. And what's the quotient rule say? If you got a quotient, you take the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. That's the quotient rule. That's what you use when you have a derivative of a quotient. Okay, great. No problem. Now, what about if you have a really complicated function? What if you got a function that looks like this? It's got insides. It's got guts right in there. So you've got something like this, and you want to take the derivative of that. What do? Well, you got to use the chain rule, folks. This is a thing that you can chain together. There's an inside, there's a blop right here, there's a whole big blop there, and then you've got an outside. So take the derivative of the outside. So the derivative of sine of blop is actually cosine of blop. So it's cosine of BLOP, and what's the BLOP? The BLOP is going to be 3x cubed plus 1, and then you multiply that by the derivative of the inside, and the derivative of that turns out to be just, let's see, 9x squared plus 0. And so there's the derivative using the chain rule. The idea is to peel off like an onion. Just peel off. Keep peeling off the outside until you get to the inside. Always remember, though, when you take the derivative, if you have sine of BLOP, the derivative is cosine of the BLOP. Don't put the derivative in there. Put the BLOP and multiply by the derivative of the inside. That's the key to the chain rule. Now we got the chain rule. Okay, but what about when you have functions that aren't functions? Like what if you have things that are relations? Like x squared plus y squared equals 1, like a circle. How do you differentiate that? How do you find dy dx there? Well, the answer is we use something called implicit differentiation. Implicit differentiation, how does that work? Well, you've got to remember that dy dx, that's an object. That's a noun. And d dx is a verb. It's a commandment. Take the derivative with respect to x. So you differentiate this with respect to x, and what do you see? Well, you see something that looks like this. What you do is you say, okay, I'll take d dx of x squared plus y squared equals 1. The derivative of x squared with respect to x is just 2x, not a big deal. The derivative of y squared, remember how I think about this? I think about this as clumping all this together. And I see this as a BLOP squared, so I actually use the chain rule, which we just developed, and the chain rule says the derivative of BLOP squared is 2 BLOP, and then I multiply that by the derivative of the BLOP, which is the derivative of y with respect to x. That's called dy dx, folks. The derivative of 1 is 0. And now you can actually solve this for dy dx by bringing this to the other side. That'd be a minus 2x. You divide by the 2y, and you see dy dx equals minus x over y. And there's the answer. So that's implicit differentiation. Just go right through and differentiate implicitly. When you have a relationship, you can still find the derivative. Great. We're making progress here, folks. We are cutting through this stuff. Well, now that you have derivatives, what can you do with that? Well, if you think about it as a velocity, you get instantaneous velocity. If you take the derivative of velocity, you actually get the change in velocity, which is acceleration. So we get acceleration now. We get velocity. Acceleration is just the second derivative of the position. So we can actually take derivatives upon derivatives upon derivatives, as many derivatives as you want. So it's great. We can do that. So higher order derivatives, no problem. What can you use these things for? Okay, we know it's true for velocity. We can use it for velocity. What else can we use it for? Well, it turns out you can use it for linear approximation. Suppose you got some wacko function. You got some wacko function like this, woo, and you actually want to figure out the value right here, and you don't know what that value is. But you know nearby there's a point that you can actually compute. So what do? You find the tangent line approximation because you remember that the tangent line closely emulates the activity of the function. The tangent line closely emulates the activity of what the function is doing, so they look the same there. So if you find the equation of the tangent line and then plug in the mysterious point, then you're all set, because you can approximate the value by plugging into the tangent line. So how would that look? Well, that's called linear approximation. Here's the formula, but don't bother memorizing it, just think about it. What you've got to do is you've got to find the equation of the line that's tangent at the known point, which is x here in this case, and this is going to be x plus delta x. The known point plus a little teeny offset is going to be approximately equal to the derivative times the change in x times the function. Plus the function. So that's it. That's the whole thing right there. Linear approximation allows you to actually compute things. Computers actually work this way. Computers know calculus. Everyone knows calculus. You've got to know calculus. Okay, now, what else can you do? Well, suppose that a derivative were to be 0. Well, how could that possibly happen? That could possibly happen because maybe the function goes like this, and I see the tangent over here has slope 0. Or maybe the function goes like this, and I see the tangent has slope 0. In particular, if the tangent equals 0, maybe we have a max or min. Also, maybe the slope or the tangent doesn't exist. Like if we have a wave kind of thing, a cusp, very pretty cusp like the waves. Well, that might be a max, that might be a min. So in particular, you can find out when objects are maximized or minimized. You can find the maxima or the minima very easily by using calculus. What do? You take a derivative and you see where it equals 0 or where the derivative doesn't exist but the function does. Those give you candidates for possible max and min. And what can you use that for? Well, you can do all sorts of max-min problems. You want to maximize profits, you want to minimize cost. Oh my God! 20 minutes? No. It's only 10 minutes left. They're trying to fool me here, folks, but I'm not going to go up for it. 10 minutes are left. Okay, so you want to maximize cost, you want to minimize cost, you want to maximize profit, you want to maximize area, you want to minimize volume, whatever it is, set up the problem really carefully, figure out exactly what you want to optimize, take the derivative, set it equal to 0, solve, find out where the derivative is undefined, and you've got it made. Really not a big deal. However, you should always remember and never forget the fundamental method of solving problems. So remember how you solve all of life's problems. The first thing you have to do is understand what you're being asked. You can't answer a question that you don't understand. The next thing you do after you understand what you're supposed to find, what you're being asked, is figure out what you know. List every single thing that you know, every single fact. Maybe superfluous, maybe you don't use it. Who cares? Write it down, understand it, make it your own. And then the last thing is take the information that you know and see a relationship between that and the thing that you seek. Try to find a connection. Once you got the connection, then you're on the road to actually finding the solution. That is the simple method for finding any single answer to any single problem. Another application, if we think about derivative as a rate, is looking at related rates. Suppose, for example, that you actually have a ladder, for example, that's falling down. The ladder is falling, and you don't want to be sued, but the only thing you do know is how fast the bottom is falling. You want to know how fast the top is falling. What you need to do there is if you know this rate, you can find that rate by linking them up with a connection. In this case, a connection would be the Pythagorean theorem. You could take the derivative with respect to time, because here you see the variable, the thing that's independent, that's always changing, is time. Time keeps on ticking into the future. So you keep going like this, you actually solve this, take the derivative using implicit differentiation, differentiate with respect to time, and plug in what you know how this is changing, and that tells you how this is changing. Pretty cool. That's called implicit, that's called related rates. Suppose, for example, you drop a stone into a very, very still pool. You have a ripple effect. Those make concentric circles that are getting larger. If you know how fast the radius is changing, you can find how fast the area is changing because you have a connection between area and rate. Area equals pi r squared. So there you go, related rates. If you know how one rate is changing, you can find out how a related rate is changing. Okay, what else can you use the derivative for? Well, the other thing you can do is actually graph really, really accurate pictures of functions. Finally, you can figure out that a parabola looks really pretty and bowl-like, like this. And it's not something really exotic, but it's just a nice pretty bowl. How do you do it? Well, you just start taking derivatives and analyzing things. First, you find the critical points. Those are points where the derivative either equals 0 or the derivative is undefined, but the function is defined. So, for example, in these examples right here, you'll notice that the derivative equals 0 here. The tangent is horizontal right there. The tangent is horizontal here. In this example, the tangent is horizontal here. And then where does the derivative not exist? The derivative doesn't exist here, and the derivative doesn't exist there. Those are candidates for max and min. Those are called critical points. Then what do you do with those things? Well, you set them up on a little number line on the x-axis, and you look at the intervals all around it, and you see whether the derivative is positive or negative. If the derivative is positive, that means slopes are positive, so the function must be increasing. If the derivative is negative, then that means the function must be decreasing. So you can see that the function, for example, here is decreasing, 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 then increasing. Here you can see it's increasing, 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 then decreasing, then increasing. So you can see where it's going up and where it's going down by the sign of the first derivative. That also determines whether you have maxes or mins anywhere, and that's called the first derivative test. Now, how do you figure out the curvature? The curvature is given by the rate of change of the derivative, how the derivative is changing. So what you do there is you take the derivative of the derivative. So you look at the second derivative, and that where the second derivative is 0 are potential points of inflection, points where the concavity changes. This is concave up, it's curving upward. This is concave down, this is concave up. So the cup is sitting up, the cup is sitting down, concave down. So here you would see the second derivative is positive, then the second derivative is negative, it changes here, now it's sitting up, it's positive, positive, we're concave up. Here we're concave up, second derivative is positive, now here we see it's concave down, second derivative is negative, and second derivative here is also negative. This is a cusp point, the derivative doesn't exist there, this is a point of inflection, this is a point of inflection, this is a point of inflection, and that's a minimum. So just by taking derivative and then second derivatives, you can actually figure out and graph a very accurate sketch of even very complicated, almost scary-looking functions. By the way, if you've got fractional exponents, expect cusps. That's my warning for the day. Okay, now, if you've got really exotic functions that have denominators, then actually you may have asymptotes. So don't forget that a vertical asymptote is where the function, after you simplify it, the bottom equals 0. So wherever the bottom equals 0, after you simplify and reduce, those are going to give you your vertical asymptotes. Horizontal asymptotes, you take the limit as x goes off to infinity, as you go off to the horizon, and you see what y value you're trying to land to. If you're landing somewhere, then you know you've got a horizontal asymptote, and it's at y equals that value. So you can put in the asymptotes, and then you can do all the other calculus, get the curvature, see exactly what the beautiful picture looks like. And that was the end of differential calculus. Great, no problem. Now what? Well, now we move on and look at the exact same thing we just did backwards. So we look at Math Jeopardy. Oh my goodness, I have only only 5 minutes left. So Math Jeopardy, here we go. So the idea is, if I tell you what the derivative is, how can you find the function whose derivative is that? Well, this is the notion of an antiderivative. So how do you actually find antiderivative? Well, we saw the formulas for that. If you want to find the antiderivative of x to the n, it would be x to the n plus 1 divided by n plus 1. Take the derivative of that and see you get x to the n. Unless n equals negative 1, then you're looking at the integral of 1 over x. And what's the integral of 1 over x? Well, it's the natural log of the absolute value of x, because the derivative of natural log we already saw was 1 over x. So great. Now, how can you find exotic integrals? Well, remember that d dx represents differentiating with respect to x, and so therefore the integral with respect to x represents to integrate with respect to x. Now, if you have a very complicated thing there with an inside and outside, you might be able to untangle that, which potentially was made by the chain rule, by using substitution. Let u equal some big blop, and the big blop's derivative should appear somewhere else in your integral. If you've got that, it sounds like a good candidate for u du substitution, and then you've got to change the dx to du by taking derivatives and seeing what du equals in terms of dx. So that's the u du substitution. You got that going on here. And now what you can do, you can take that and look at studies of motion again. Now I can give you acceleration. If you integrate, you get velocity. If you integrate again, you get position. So vertical motion, not a big deal anymore. Lands, no problem. Things moving at space, like this thing here. Watch it, folks. Woo! You can get that. You can try anything that moves, anything at all that moves, we can now analyze whether you have crabs or whether you have a bike. It's not a problem anymore, folks. If it's movement, we can anti-differentiate it and figure out what it is. Not a problem. Now, where does this lead us? Well, it brings us back to the very first question of the course, which was, how do you find areas under curves? We have to answer that. We haven't done it yet. It turns out the surprising answer is that it's the fundamental theorem of calculus. And the idea is, if you want to find the area under this curve from A to B, right here, if you want to find that area, then how do you do it? It turns out that if that function is called, let's say, f of x, then all you do is integrate from a to b f of x dx, because you're summing up little rectangles in here that are base, small change in x, base times height, which is the function. You go from a to b, and this equals f of capital F of b minus capital F of a, where what's capital F? That's the antiderivative. So if you take the derivative of capital F, you actually get little f of x. So just find the antiderivative, plug in the big point, plug in the small point, subtract. That will always give you the area under the curve. You could look at areas of more exotic things. For example, if the thing actually goes like this, then actually, this is actually not very x-easy. The rectangles aren't very clear. The rectangles change from going from green to green, over to green to orange, then to orange to orange. It's not very uniform. However, if you put the rectangles in this way, and stack them this way, now you're summing with respect to y. And so here you would actually sum this with respect to y, so you would integrate this dy and put the rectangles in this way, and you put the rectangles in that way and stack. You'd stack from low to high, and you'd stack the rectangles like this. Okay, that is all of calculus. I did it in under 20 minutes. That's what it is. Go back, think about it, have fun with it. Congratulations, folks. You just finished Calculus 1. Have a good time, celebrate, good luck in the final. Bye.
What are some functions you didn't even talk about? Yeah. We talked about derivatives of ln, you talked about derivatives of powers, you talked about derivatives of fractional, like radical. You didn't talk about trig, and definitely not trig inverse, right? Yeah. You didn't even touch on that. So is that enough to pass the AP exam?
Yes. You should put it at the beginning of the year and then again at the end, so everyone's like, we understand now.
Yeah.
But at the beginning, you would all just be like,
Yeah.
that's true, that's true. To show you how much actually makes sense. I understand. I know. I could do like Mrs. Hill and try to do a full-length AP calculus exam at the beginning, but you'd all just be like,
Oh my god. I missed that.
oh, she doesn't anymore? Never
I think she did. She like a diagnostic kind of thing.
Oh, she doesn't.
Yeah.
It used to be a full-length one, but maybe that was just never mind. Okay, so I just changed it. What do you have in front of you? An FRQ. Are we going to get to it? Yes, but right this second, no. Hold on and pause. I want you guys to turn in the back of your spirals. Ooh. Turn in the back of your spirals. People that gave in your spirals late, just get a piece of paper. For right now.
Really?
packets, if you haven't yet, sorry, I didn't put it back there. AP packets for chapter 6, pass them back, pass them over. Some people have already started putting them in your tray. So if you guys have your AP packets and you haven't turned them in yet, go ahead and pass them back, pass them over, turn them in. All right, in the back of your spirals, I want you guys to start a nice clean sheet. Put AP exam review, and then I want you to put limits. Yeah. A and B, sorry. A and B, and possibly to finish FRQ number 1 if we don't get to in class. Can you guys understand if I say Y, W, S, Y, T? When you see, you think.
When you see, you think.
Got it. So for tomorrow, when you see, you think A and B, and if we need to, we'll do FRQ. So whatever we don't get to finish. All right, you guys have it back in your spirals? AP exam review, limits? Yeah, if you guys want, just make sure I get it back. So if you want to do that, you can do that too. Okie doke, here we go. I have 5 multiple choice and then there are 5 answers and we'll see if we can get them right. Number 1, write down the problem. It'll be on the video as well if you want to come back and reference it. We have a limit as x approaches infinity. So on a graph, where are we going? To the right. Good. Guys, you're going to have to talk about this in your limits. I think it talks about infinite limits in your when you see, you think. What do we think about when we're thinking about infinite limits? Plug in. Factor? It already is factor. Fuzzy math. Think about plugging in infinity, but aren't we going to get infinity over infinity? We have to ask ourselves, do the degrees of the infinity tie? Yeah. Or does the top win or the bottom win? If we have infinity over infinity, to what degree? Right? What do we have on top?
Infinity times negative infinity.
We have a squared, a quadratic, right? What do we have on bottom? Okay, so if it's a quadratic over a quadratic, the degrees of the infinity are tied. The degrees, the exponent is tied. What do we do when the degrees are tied? Degree test. Well, we already did that. They're tied. The ratio. So do you even have to waste time on, say, AP exam? I know the orientation is off. Someone bumped it this morning. whoever you were. What's my x squared term going to be on top?
Negative 2 would be.
Who cares about the rest? I only care about the highest, right? What's going to be the bottom?
X squared.
Question, what's my final answer? We'll see if we're right. Number 2. Yeah.
You got that from.
Foiling.
Oh.
So basically, when I looked at my foiling, I figured out where my x and x was going to be. It was going to be on the outer, so I multiplied outer and then I multiplied first. Because I only cared about the biggest. Does that make sense? But, kiddos, what would have happened if you had FOILed it all out and then found the highest ones and circled them? They would have been tied, and they would have been those 2 terms. You guys, start looking at number 2. I'm coming to you. Oh, hold on. Start looking at number 2. What are the horizontal asymptotes? P.S. On the AP exam, you want to take about 1.2 minutes per question. Random. FRQs, you have 15 minutes theoretically for each one. Hopefully some will take shorter, so you can take longer on others.
That's a cool question.
Which you could think of as 5 minutes per part approximately, but some parts are easier, some parts are longer, so it's hard to time yourself.
Is time like a huge thing? Because there's some people who are like, if you don't plan it out, you'll die. But if you don't really plan it out, you'll be okay.
For the most part on the AP Calc, some FRQs you're going to like and some you aren't, so as long as you learn the important task of, on a multiple choice, if you can eliminate something, you've already thought through the question enough to try to finish it real fast, and if you're like, I don't even know what to do, you better be skipping it and coming back. So usually it's more you get through the whole thing, but you might have some along the way you didn't get back to. Same thing with FRQs. But usually on the FRQs, people have enough time. If they get confused because then they're like, next one, next one. I don't know what to do. But hopefully not for you guys. I suppose, I don't think you want to take a derivative until you FOIL it out, and if you can, once you FOIL it out, realize the degrees are tied, it saves you from having to take derivatives. Does that make sense? Yeah. But you wouldn't have wanted to do product rules. Kiddos, how do you think about horizontal asymptotes? It is a horizontal line that the graph will eventually approach as you go to the right, to the left, which it means as you go to infinity. It's just a limit to infinity. And negative infinity.
Isn't it? Do you set the, no, you don't set the bar equals to 2?
That's vertical asymptote. One of the most commonly missed limit questions if you understand limits. Horizontal asymptotes. Usually the limit as you go to infinity and negative infinity is the exact same thing. But whenever you have an exponential, it's not. And here's the reason why. If you do fuzzy math and plug in infinity, 2 to the infinity, is that stronger than 5? Yeah. How about 2 to the infinity on the bottom? So these ones are the highest and they tie. What's the ratio of the leading coefficients? Negative 1. These are tied, just like the x squareds. What are the ratios on the outside of the function? 1 and negative 1. So right here, I have an HA at y equals negative 1. Why am I going to put a comma and say, but we got to look at this one? If you plug in approaching negative infinity, if negative infinity is in a power, what is that doing to that poor little 2? 1 over 2 to the infinity. 1 over 2 to the infinity, 1 over 2, 1 over 4, 1 over 8, 1 over 16, 1 over eventually something a whole lot bigger. Who's stronger, 5 or the poor little 2 that keeps on getting cut in half and cut in half and cut in half and cut in half? They win. They're going to 0 if you plug in negative powers, because it's 1 over 2 to the x. If it's a negative exponent, 1 over 2 to the x. So therefore, what's my other horizontal asymptote? But wouldn't you have felt really good answering A if you kind of knew how to do it? AP at its finest. Number 3. Oh, hey, we're not going to infinity anymore. What are we going to? 0. Okay, whenever we take a limit as you approach a constant, we're getting, remember his little fingers, getting closer and closer. What do we always try to do mathematically? Plug it in, plug it in. What do we get?
Keep going.
Now, right now, we could keep going by like factoring and canceling out and trying to do fun stuff like that, or we could do what Ellis said a second ago. What's that little guy that helps us with 0 over 0? L'Hopital's. Whichever one you'd rather.
L'Hopital, pull out the x squared.
Pull out the x squared, that's what I would probably do. You pull out the x squared. Hopefully you guys see they're just going to cancel, right? We end up with 5x squared plus 8. And we end up with 3x squared minus 16. Well, now what?
Plug it in.
Oh. Plug it in. But L'Hopital's would have worked, right guys? Sometimes it's faster, sometimes it's not. When you plug it in, you get 0 plus 8 over 0 minus 16, which is negative. You guys agree? This is algebraic manipulation old school, and it was faster than L'Hopital's. But what would have happened if you had taken some derivatives? 20x cubed, 12x cubed, and then kept on going? You would have gotten the same ratios. Yeah.
Did you just do the test, the
Degree test.
degree test?
Because 2 to the infinity and 2 to the infinity, that's 2 to the 2, 3, 10, 100. That's way stronger than 5 and 1. So when you're going to positive infinity, those win. The ratios were 1 and negative 1. But for this one, 2 to the negative infinity, 2 to the negative infinity, that's 1 over 2 to the infinity, 1 over. Those are zeros, the 5 and the 1 win. Such a that ratio. Does that make sense?
You separate it when it's exponential.
Whenever it's exponential. Otherwise, you're pretty much safe just doing the old-fashioned, do it to infinity and got it. All right, 2 more. I don't think we'll get to continuity today, but that's okay.
Oh.
Woo! It's a favorite. 1 and 2. At least there's not a K this time. This has to do with limit and continuous and differentiable all at the same time. The wording is misleading for number 1. Get your function down, and we're trying to figure out these 3 statements, which are true. Limit exists. Limit at 2, continuous at 2, differentiable at 2. It says limit at 2, but what should I really be saying? Limit as x approaches 2. We don't care what's going on. There could be a hole. Cover that. Remember, look outside the window. Or through the window, whatever.
Yeah.
Is there a limit as I approach 2?
Yes.
I think so. Couldn't we just do L'Hopital's and say 0 over 0, but wouldn't that be 2x over 1 and then plug in 2? What's my limit? Oh, too fast. Lo siento. Limit as x approaches 2? Could we factor? Yes. And reduce? Yes. Could we also see 0 over 0 and say, fine, derivative of the top and derivative of the bottom? Both ways work. I just happen to do L'Hopital's so that you guys can remember L'Hopital's. Now we plug in and say, oh sweet, the limit is 4. Does the limit exist? The answer is yeah. So right away, if you can figure out 1, even if you're stuck on the rest, how have your chances improved? Pretty good. You had a 20% chance, now you have a 33% chance. It'll get better if we can narrow anything else down. Is the function continuous? Ooh, no.
No.
Why?
Yes, the function is
Well, there's not a, there would have been a hole if it said x equals 2, but it says, okay, this is true everywhere but x equals 2. What's going on at 2? There's a hole there, and is it filled in? It's filled in somewhere else, that removed point. So the question is, does the limit as x approaches 2 of f of x equal f of 2? Definition of continuous. Hey, sweet. So far I can go ahead and, oh my goodness. Who cares about the last one? I'm done. Dun, 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 dun. Process of elimination saves you time. True? Yeah, so the function is not continuous. Can it be differentiable? Forever card on that. Last question.
So there's always going to be a limit if the one-side limits agree, even if it doesn't exist at that point.
Right.
Okay.
Right. Remember, like what he did, cover the hole, cover the spot, what's going on. The 2 cars, are they meeting even if it's burned down
Right.
or closed?
I remember that video.
It's a good one. Look guys, an old-fashioned limit graph.
Yay, 1 degrees.
Which of the following are true? If you guys can't read, get your graph down. I have limit as x approaches 2 little negative, limit as x approaches 2 little positive, limit as x approaches 2. Ooh. You can tell me a yes or no on one of these.
Limit doesn't
Yes.
exist because we're not going at the same time.
Ryan's saying 3 is a no way, Jose, because they're going different places.
But the other 2 is just.
1 is true, because as you come from below, is this guy headed someplace? Yeah. He's not going infinite, he's going out. His is burned down, and they've relocated. The other guy got the memo on the new address on Yelp, right? But 1 is true, 2 is true. But just by figuring out that they don't exist, you already narrowed down D&E. But just a few of you would have felt really good saying only number 2 is true, or none of them. Well, that's not even an option. Let's check our answers real fast. You guys have the letters, right? Real quick, and I'll come back. B-E-A-A-C? Nice. What did we review in multiple choice today? Limits? Pretty much.
Yeah.
Infinite and to a constant and L'Hopital's nice. And a little bit of continuous and differentiability. Question, kiddos, what do you have that I gave and handed out to you?
FRQ.
The first question of an FRQ. How many sides does it have? Do you see how the AP does it? They give you a nice big room and say, okay, solve just this part here. But is it all one question? Yes. They've just given you different boxes for different parts. Here's your homework, just so that we're not going to finish it in 2 minutes. I want you to try to do that FRQ tonight on your own. We might even just exchange them within class and let you guys see the answer key for this one tomorrow. Does that sound good? So you can remind yourself of the points you get. And then we'll do some more multiple choice practice on probably continuous and then derivatives. A and B.
Chemistry is nasty. You have the FRQ, they just give you one sheet, so all your math has to be done in one. It's terrible.
Oh, that's rough. I don't
I
think
hate it.
that
All of that, so we have like 4 4-pointers and 3 9-pointers, but the last 4-pointer was just